All right, well, I will begin with a word of prayer. Dearly Father, we thank you again for this day and for your creation, and we thank you for math. Help us to understand a little bit more about tangent spaces and push forwards and all these constructions, and just give us wisdom, Lord. In the name of my prayer, Lord Jesus. Amen. See if I can get my computer to actually wake up. Again, my apologies for not getting started earlier. Good. Let's see here. Advanced calculus, I think it's I seem to have closed everything. I got to find my 2015 folder, I think, right?
Yeah.
2015.
Section 10.2.
Section 10.2, you say? All right. All right, so we're talking about tangents as derivations, and we've proved that they satisfy all the usual rules of calculus, even the chain rule. And so I proved that the derivative of a constant, or a derivation acting on a constant, gives 0. And proposition 10.28, I think, is where we finished, namely that if a derivation that if we have two functions are equal, then the derivation will also give the same value. Let's see here. And then that led us to proposition 10.29, which I mentioned is a not as easy to prove thing. So let me just state it. So suppose xp is an element of the, already forgot my notation, derivations at p of the manifold M, then if x, is chart at p, then xp is equal to a sum, I equals 1 to m, I guess, of x sub p of x upper I partial xi at p. Proposition. And again, this is proposition 10.2.9 on my page 227 of my 2015 notes. So let's see here. So I have a lemma before then. What's my lemma? My lemma, oh man. See, Ernesto, I printed these notes out and I've left my printed notes in my office. This is just the worst day. I will resist the urge to walk back to the office and burn another 5 minutes. All right, so here we go. Lemma. We have f, a smooth function. Let's see here. All right, fine. It's not the greatest, but it's a way. So here's my lemma. We have f from m to r, smooth function. Right?
Which lemma is this?
Lemma 10.2. Right after this one. It's right under this proposition on page 10, lemma 10.2.10. So if we have X is a chart, all right, and it has X of P is equal to 0, all right, then there exists G sub J from the manifold to the reals with G sub J of P equals to partial F partial X sub J of P, all right? Moreover, for Q close to P, we have F of Q is equal to F of P plus the sum K equals 1 to M of X upper J of Q times G sub J of Q. So I say this follows from proving a similar identity on Rm and then lifting it to the manifold. I leave this as a non-trivial exercise for the reader. It can be found in many texts, for example, Burns and Gideon, page 29, or Lawrence Conlon's differentiable manifolds text, which is a really condensed but well-written text on manifold theory. It's on page 49 of there. This lemma only is true in the smooth category. It only holds in the smooth category. There's a in the details of proving this lemma, you need the smoothness. And it's one of those things that involves an explicit calculation from like the fundamental theorem of calculus. This is kind of like a Carathéodory type formula. Did I ever show? Oh yeah, we did that in complex. So it's kind of like that. I mean, if you want to think of it in that regard, this is kind of like the phi, you know, and this is like the z minus a, but it's based at 0, so it looks like that. Very fuzzy, but roughly speaking. Anyway, so there's that. And I'll probably give you that as a homework since you'd probably be interested in that. But I will try to get you a scan of the relevant book so you can just kind of work through. You don't want to try to prove that on your own. You don't have enough time. That's something you want to follow somebody on. So anyway, once we have this lemma, I think it's relatively straightforward. We use the lemma, assume that xp equals to 0 and that the g sub j at p is equal to partial f partial x. So we calculate xp on f. All right, so that's really xp on what? So we can write the formula for f as f of p plus, you know, the sum k equals 1 to m of x upper j of q gj of q. Right, that is what we're feeding into the derivation. And then by linearity, we get what? By linearity, we've got xp of f of p, right? And then plus the sum k equals 1 to m of xp acting on what? Xp acting on x upper j of q times gj of q. So here, you know, this notation is a little bit, you know, funny. Like we're writing the dependence of the function here, whereas I wasn't over here, but it's you know, admittedly a somewhat lopsided notation that I'm using. If you can forgive me. This is a constant, so this is 0, but this is a product of functions. So we have what? We've got the sum k equals 1 to m of x sub p of xj, right? And I'm now going to omit the of q, which is annoying, but I'm going to do it. And then g sub j of p plus, x sub j of p times x sub p acting on the g sub j of q. Well, I'll omit the q arguments at this point just to be annoying. But at p, by construction, x sub p is, we're using the lemma, right? So this is 0. And, that's the assumption here. And on the other hand, this at p is what?
Partial.
Right, it's partial f, partial xj at the point p. So of course then we can look at this, we can peel out the, look at it as a sum of operators, right? Oops. Oops. Okay, at p, all acting on f. And there it is. Since that holds for all f, that proves that the derivation can be written as a linear combination of the coordinate derivations. All right? And so it's also worth noting, if we had another coordinate system, right? We could also write xp as what? Like the sum, say, j equals 1 to m of xp of, oh, maybe not j, let me use I here. Yi, partial yi at p, right? We could also, if we had two coordinate systems, we could write that, right? But xp itself is geometric, right? So this is equal to this, right? And okay, so how can we express the components of the vector in one coordinate system versus the other? Well, the components of the vector, what are the components? It's x sub p of x upper I, right? That's the components of xp in the x coordinate systems, right? So if I want to calculate the coordinates with respect to the other coordinate system, right? If I just take this bottom equation and I let it just act on, remember what we proved last time? That if I hit this with like, let's say y sub k, oh, maybe not k, y sub, I've got an I, I've got a j. Oh, what the what? Look at that. Put a j here, right? Come on. That was not good. So, okay, now I haven't used the k, so let's put a k up here. Oh, if I do that, well, this is a Kronecker delta, ik. So this just becomes x sub p of yk. And what's that equal to? Well, it's equal to a sum, j equals 1 to m of, all right, you're dead. You're dead. Of, xp of xj, right? Partial y k, partial xj at the point p. So I told you this like maybe a couple, like 2 weeks ago or so, that the partial derivatives were going to be the coordinate change matrices. Well, now you see it happening, right? This is the coordinate change matrix. Coordinate change matrix, if we want to look at it as a matrix. for switching from one coordinate system to another for the components of the vector expressed that way. All right, so with all of this in mind, we'd make a definition. Definition, the tangent space at the point P of a manifold M is just going to be dpm, which you could also say derivations, you know, at the point P of M, if you like. So that's our definition of tangent space to the manifold. It's the set of derivations at the point. All right, so now that we got that, and I tried to explain the geometry of this more last lecture, so I'm going to leave it there, as I doubt I would add any value if I tried to rehash that at the moment. So let's, now that we have this definition of tangent space, what can we do with it, you know? Well, the first thing you maybe want to do is extend the concept of the differential. Like the Fauché derivative. I mean, what happens with this Fauché derivative in this context, right? So that brings us to our next definition, which is the differential for manifolds. So in particular, if I have m and n smooth manifolds of dimension m and n respectively, so suppose I've got f, a mapping from m to n, where m and n smooth manifolds, dimension of m equal to m, dimension of n equals to n, all right? Then we define dpf as a mapping from the tangent space at p to m to the tangent space at f of p to n. This is the differential of f at p, and we define it for each derivation to m at p and for each smooth function at f of p. For each xp in the tangent space to p at m and g in the smooth functions at f of p via. Here's how it goes. So dpf, all right, acting on xp, that acts on g. How does it do it? All right, how does it do it?
Compensation.
Oh, sorry, I'm confused all of a sudden. Why do I have two definitions?
They say so.
I think that's a duplicate definition. Goodness gracious, what on earth? Oh, this is all duplicate. Look at that. Whoa. Does it keep duplicating? No. It's just, that's funny. So my notes are just like, it's deja vu all over again, right? All right. So this is one of those places where I think the book we're using next semester is a little bit better, in that it makes a clear distinction between push forward and differential. So I'll leave that to be better exposited there, but I think the push forward is for vector fields, whereas the differential is for vectors, if I remember right. But again, if I mixed it up, my apologies. The formula here has to be the following. It has to be xp acting on something. Well, what can it act on? xp acts on what? It acts on smooth functions at p. How do you get a smooth function at p from a smooth function at g? Well, g maps from where to where? G maps from, well, from N to the reals, right? And then F maps from where? M to N, right? So can we compose these? I think we can. We can do G composed with F, see? And then that will make sense because let's see here, because G composed with F, F goes first, so we go from M to N to R. So G composed with F is actually a mapping from M to the reals, right? And more than that, it's going to be a smooth function because we're assuming that F is a smooth function on manifolds, all right? Which means that the local coordinate representatives of F are smooth, which then in turn means, since G is also assumed to be a smooth function, that altogether the local coordinate representative of G composed with F will be smooth. And so that's a reasonable definition. Then for it to be a truly reasonable definition, we need what? We need that, we should check that what? We need, so that's the definition. But for it to make sense, we need that dpf of xp is an element of, the derivations, if you will, at f of p of n, right? Or I would just call it dfp, but I'm writing out derivations just so it's more friendly. Is that the case, right? So what do you need? You need it's linear and it's Leibniz. Is it linear? Well, it's pretty manifest that it's linear from this formula. And the Leibniz also follows because you have the product rule for xp, so you just do the product rule and then look at the composition. So yeah, it works. And so I say dpf is called the push forward. That's probably not quite accurate. I think really perhaps I should not do it for just one point, but for lots of points. And then I would be, taking a vector. Let me draw a picture. So if on M, right, and over here's N, if I had like a vector field, well, first of all, if I have just one vector, let's say xp, right? Then over here, you have dpf of xp, right? And I draw that somewhat schematically. It's technically in the tangent space to M. It's technically in the tangent space to N, which are abstract sets of derivations now. But if you had not just one, but you had like, a vector field on M, an attachment of a vector at each point, then that would, of course, likewise induce a vector field over here. The trouble you get into is if your function, right, is not one-to-one, you could have the situation, but you will have the situation that it goes back to one point more than once, right? And then the push forward would push a vector from each of its pre-images, and they wouldn't have to match up, which means you wouldn't be attaching one point to each point, wouldn't be attaching one vector to each point in your codomain, but possibly two. That wouldn't be a vector field. The vector field's an attachment of just a single vector at each point along an object. That's a vector field, So, yeah. But anyway, that's the differential for manifolds. I think it would be good for us to try to do a calculation, right? That would be a healthy thing for us. So the next thing I do in my notes is just to show that this actually, if you look at the case of F being coordinate change on like R2, you can understand this is exactly the story of like changing partial derivatives with respect to R to partial derivatives with respect to X and Y, or vice versa. Like, in other words, you can view this as the problem of changing partial derivatives with respect to coordinate change. If you look at the coordinate change map, maybe I should do that. Yeah, let's try that. Example 1. So basically, I'm having M equals to N equals to, let's say, R2 sans the origin, like the punctured plane, because you know, I'm just trying to be polite. The polar coordinates, they don't work at the origin, right? And in fact, maybe I should throw out, you know what, just for the sake of specificity, let's get rid of this. Let's instead go with like x comma y, such that x is greater than 0. That way I can write formulas for the angle without blathering too much. So that positive half plane is a nice context here. And great. So if I want to, I can think about, I like to think about it in two pictures though. So, I mean, while they're equal as point sets, I'm going to draw two of them, which I understand is kind of a little bit funny, but you'll forgive me. That keeps my picture from being too busy. So we'll do, I guess we'll do r theta here, and we'll do xy here. I mean, we could go either way, all right? And then what's my map? My map is going to be f of r theta, right? Let's see here. So let's try this out. So we're going to try the differential of f at p of, well, we'll feed it our partial r. And I'm going to, well, fine, at the point P, wonderful, at the point P. And we're going to let that act on, well, let's be smart about this, right? We know over here, according to the lemma and the proposition we started class with, we know we can build any vector from what? Like, what's a vector in here look like? It looks like v of x, partial x, plus v of y, partial y, right? If you think about v being my x sub p from the start, right? And I'm suppressing the point dependence for a moment. So to figure out this component, I just act on x, right? Act on the x function. But that by definition is partial r acting on what? G composed with f. X composed with f of r theta, right? All of this at the point P, right? What is x of r theta? What does the x function do? It picks off the x, so that's you know, partial r of r cosine theta, which is cosine theta, right? And likewise, if we let this thing hit the y, what do we get? Well, y picks off the r sine theta, right? So we get sine theta. So lo and behold, what we have then is partial r at the point P is actually equal to like cosine theta partial x at the point P plus sine theta partial y at the point P. And through a very similar calculation, you can show that the theta derivative pushes forward under the polar coordinate change map to minus r sine theta partial x at the point P and plus r cos theta partial y at the point P. And we can just as well look at the inverse coordinate map, right? And study the push forward with respect to the inverse coordinate map if we're so inclined. Yeah? Because the inverse exists, because I've been careful to, make it an honest coordinate change. And I guess I can work down here. So what's F inverse? F.
X, Y.
So we got what? Square root of x squared plus y squared, right?
Tangent inverse.
Yeah.
Over X.
Tangent inverse y over x, right? So if I look at the push forward, and instead of p, let me use q since it's technically f of p, right? I'll just use q for the sake of not writing a bunch of junk. But the push forward at q of the inverse of, well, so here we should be looking at perhaps, how the x, partial x is like here, right? So like, think of it this way. Partial r and partial theta live here. Partial x and partial y live here. And so if I push partial x back, to understand how it acts, I let it take a bite out of r, I believe. Yeah, I fed it x before, now I feed it r. But that is literally partial x of r of the bit of xy, right? At the point q. But r of xy is the square root of x squared plus y squared, so that gives us, x over the square root of x squared plus y squared, right? Yeah. But if I'm expressing that, then in the coordinate system over here, I would write that as, what? Did I do the F inverse? I should say R of F inverse of xy, right? Sorry. But R composed with F inverse of xy. Well, F inverse of xy is this, and R of this is the square root of x squared plus y squared. And if I differentiate that, I get that, I believe, which, if I haven't done this wrong, well, it's that. Which I guess is cosine theta. And let's see here, d q f inverse partial y. My apologies in advance if this is all nonsense. I wanted to let that act on theta, right? So that's partial x of f inverse. No, I'm my bad. Theta, the theta coordinate map, right? Composed with f inverse, and we're looking at it in xy coordinates in this partial derivative evaluated at q. But I believe that is partial x of, well, what's f inverse of xy is this, and the theta picks off the second component in this notation. So that's literally inverse tangent of y over x if I sort through the notation here, which is, like minus y over x squared plus y squared when you sort it out. Multiply by y over y. Well, multiply the x squared through, I think I want to say. But anyway, that is exactly what? That's exactly minus sine theta, I think, over r, isn't it? So what this all shows is that if you want to express partial x at the point q, well, you can write it as cosine theta partial r, right, minus sine theta over r partial theta at the point Q, you know. But look, if you really sort through what this is doing, that's exactly, you know, that is partial x partial r, and that is partial theta partial x. So, excuse me, that's partial r partial x. Is that right? Partial r partial x. Well, I mean, I guess to be fair, I could write these in the xy formulas if I wanted. You got options. If you really take a step back and stare at it, though, what you'll find is this is exactly the chain rule that we wrote between x and y in polar coordinates. So the push forward is simply a generalization of the chain rule, is one way to look at it. The push forward is really just that. But it's more than that because it doesn't have to be just, the push forward makes sense for things other than just coordinate change maps, okay? Like it's much more general than that. Okay, but at least I agree with my calculation here on page 231. I also have the push forward of partial y. Although I feel like that's a miscalculation. It's gotta be a miscalculation. There should be a division by r. There's definitely a typo in the formula that's right above section 10.3.2. Pretty sure we should have like the you know, push forward under the inverse map of partial y. It should be like sine theta partial r plus cosine theta over r partial theta. I'm pretty sure about that. So what's in the notes right now is missing the r. Yeah. But it is plus instead of minus. The reason for the minus here is when you're differentiating with respect to x, you've got a reciprocal power, whereas when you're differentiating with respect to y, you just got y in the numerator, so it's different derivative, no minus there. All right, so next I have a pragmatic formula for the push forward. So here I give you just a gory, if you have both your coordinate systems, here's how you calculate the push forward, all right? And if you really look at it, what it's saying is to calculate the push forward, you calculate essentially the Jacobian matrix of your manifold map, and you multiply it by the components of the input vector to get the components of the output vector. It's, again, this is all an abstraction of the Fauché differential. The difference being, of course, that we're mapping derivations to derivations. But at the heart of this reduces back to the Fauché differential if we make the identification that like the partial derivative is the unit vector, right? Like if you convert the you know, the partial derivatives back to like the underlying unit vectors, if you make that identification, if you trade your active objects for passive objects, you can get back to the Fauché differential formulas if you want. So really any calculation we did before about like Fauché derivatives of, say, a matrix space or something, you could directly rip that off. Oh, I should not have probably erased what I just erased. Oh well. Oh well. I'll get over it. Okay, so let me try to redeem the day and come up with a new example. That sounds like a recipe for disaster, doesn't it? Well, let me write this handy-dandy formula up here for us and see if we can actually flesh it out. So this proposition 10.3.3, here it is. df at the point P acting on this vector, y equals 1 to m of x sub I partial x sub I at the point P. What is it equal to? Well, it is equal to a sum I equals 1 to m, a sum j equals 1 to n of the components that I had for my initial vector, x sub upper I, times the partial derivative of the jth component function of the map f with respect to xi, and that points in the yj direction at f of p. So here, what's going on? Let me just try to draw a picture of what's going on here. It might be helpful, maybe, is we're imagining we've got a manifold M, all right, we've got a manifold N, there's a smooth map going from there to there, all right. Over here, you have, at the point P, you have, x coordinates. And then over here, at the point Q, let's say equal to f of P, you have y sub j coordinates, right? So you can picture, a vector attached to P, like this maybe, right? And then that pushes over here to the differential of f at the point P acting on xp, right? If you if you like, we could call this whole thing like big upper Y of f of p, right? And then this is essentially just saying that the jth component of this, which would be y f of p acting on y upper j, right? By our theorem earlier today, that would just literally be the sum j equals 1 to n of x upper, not j, rather I equals 1 to m, I should say. I equals 1 to m of x upper I partial of yj composed of f partial xi. So that's what I was trying to say, is that really if you can look past the derivation stuff here, it's what we said before, the components of the well, to find the change in the function going from one space to another, we can take the Jacobian matrix times the change in the domain, and that gives us the change in the range. And that's what's going on here as well. It's just also with all the trappings of our current abstraction. Let me see if I can come up with an example. Let's see here. Example 2. Let me start out real easy, relatively easy speaking. Something like this. Suppose we've got f of x comma y equal to oh yeah, how about something x squared y squared xy. All right. So here I'm looking at f as a mapping from where? From R2 to R3, right? And just to make things a little bit more sort of transparent, let me use different letters for the coordinates in the range. Like instead of using x, y, z for R3, I'm going to use a, b, c, if that's okay. I'd use u, v, w, but honestly, like it's much easier to tell the distinction between a, b, and c as coordinates, right? Okay, great. So here we have really three component functions. So my y, quote unquote, is equal to a, b, c. A, B, C are y1, y2, y3 in the range. Okay? And so when I calculate like y1 composed with f, right, I have to let that, naturally I think about that as a function of xy, and that is, you know, a of x squared, y squared, xy, right? So that's literally x squared. And likewise, y2 composed with f at the point is equal to, you know, y squared. And y3 composed with f at the point is xy. So if you like, I could just abbreviate this and express these concepts as, so I could just really say that, you know, f1 is x squared, f2 is y squared, and f3 is xy. That would be a reasonable, you know, that's what we tend to do in calculus, right? We don't write yj composed with f. We just write f upper j for the jth component function when there's no danger of ambiguity. There almost never is. Okay, so if we want to push forward under this guy, right, at the point whatever, point P, let's say at the point x naught, y naught, y naught. I'm sorry, that's horrible. I regret nothing. And I want that to push forward the vector, let's see here, I need yet other letters. So let's say alpha, you know, partial x plus beta partial y, right? Where does that, what vector field does that push forward to? Well, so let's see here. Well, in order to figure out what that pushes forward to, it's most natural to let it do what? It should act on what my well, I guess the question is, do I want to use my proposition or do I want to go back to the calculational method over there? If I'm using my proposition, if I trust it, my, let's see here, I'd have like equals to xi is alpha, right? And then partial x, let's see here, of x squared partial a plus fine, alpha partial x of y squared partial b plus alpha partial x of xy partial c. So that would all be the I equals 1 part of that. And then it gets summed over j equals 1 to 3, which gives us the ABC. You might find I mean, obviously you could like factor out the alpha. I mean, you could rewrite, it might be, as a pragmatic matter, it's probably nicer to think about this as like alpha partial x acting on x squared partial a plus y squared partial b plus xy partial c, with the understanding that, well, if you want to, with the understanding that a, b, c just ride along. I don't know, whatever, but that's those terms. But, well, what did I write there? I wrote, what is this x squared partial a? Well, anyway, let me stop trying to come up with snazzy formulas at the moment and just finish this thing. And then we've got the beta term, right? Partial y. Right? And what do we get? Well, we get 2x naught alpha partial a, right? At the point what? Well, let me just say at the point q naught, and I'll say what q naught is in a minute. And then this, let's see here, that gives me 0, but this gives me plus 2 y naught beta partial b at the point q naught. And then let's see here, there's two things from that, right? Plus alpha y naught plus beta x naught partial c at the point q naught, right? And what is this point q naught? Where q naught is f of x naught y naught, right? Which is specifically x naught squared, comma y naught squared, comma x naught y naught. So there you go. This vector pushes forward to that vector. And as you can see, it depends on the point, right? Like I have to evaluate all these derivatives at the point P technically, you know. If that makes sense. Now if we want to think about a push forward, right? This is the notation that tends to be used, like f lower star of partial x, for example. What would that be equal to? So I'm putting alpha equal to 1, I'm putting beta equal to 0. So if you just look through this mess, you've got like, 2x partial a, right? Yeah. Plus y partial c, right? On the other hand, if we look at the push forward of partial y, we'd have something like, 2y partial b plus x partial c, right? And if you can imagine this, the push forward of these pair of vector fields would be giving you another pair of vector fields in the three-dimensional space. Basically, these would be tangent to some plane, so like this mapping is embedding a copy of the plane in 3 dimensions, and these would be tangent vector fields to that embedded plane in 3 dimensions, something like that. Come on, wake up, come back to me. Won't let me page down. I bet this is because of Microsoft. You know what this is? I guarantee you, I've got 300 megabytes of Microsoft Teams in the background doing something stupid right now. Where are you, Microsoft Teams? Show yourself, I know it's you. Well, maybe it's my Google Chrome. Well, computer, if you'd kindly let me scroll again, that would be lovely. Oh, yay, scrolling is back. So, like I said, the push forward is more than just coordinate change. If we compare a mapping between spaces of disparate dimension, then push forward captures something about the mapping in question and the domain and range spaces. I said, for example, the existence of a non-trivial vector field on the whole of the manifold implies the existence of a foliation of the manifold. Now I'm getting ahead of the story there, but let's see here. My example 10.34, I have a mapping from the plane to 2x2 matrices. Let me take a second here to look ahead and see if I can decide what to do here. Yeah, example 10.34 I think is helpful. It's a little more abstract, and it's let me try to do something kind of sort of like that. So we have mapping from R2 to R2 by 2. That's what I did in the notes. Let's see here. So I should mention, like, the other viewpoint for tangent spaces is like equivalence classes of curves. And there, this definition of push forward gets even sillier. It just becomes like derivative of the composite of the two paths or something. Like, so there are benefits in, to each viewpoint. And I think we will not be able to avoid that next semester. But at the moment, I am avoiding it by focusing on calculation in coordinate systems more so than like some of the abstract ways of thinking about things. And I think that's okay. So, all right, so let's see here. If we have example 3, all right, so I'll try to stick with the notes, general pattern. Actually, it'd probably be good to do a curve. Let me do R to, say, R2 by 2. So f of, let's say, t is equal to t squared, t cubed, t to the 4th power. All right? That's definitely a smooth mapping. And so we can look at the push forward, let's say at time 1 of, well, here there's just ddt. And let's see here.